Welcome once more, ladies and gentlemen, today to chapter 8 of my course on linear algebra in 2D, and we're going to explore eigenvalues and eigenvectors today. So first I'm going to introduce the concept and derive a few first properties of them, in particular how to compute eigenvectors and eigenvalues. Then we will use eigenvalues to characterize matrices and linear maps in the plane via their eigenvalues. And finally, we will briefly talk about some applications of eigenvalues. So let's first get to know them. If we're given a 2 by 2 matrix, A, and there exists a non-zero vector x and some scalar lambda such that A times x is lambda times x, so just a multiple of x, then we call x an eigenvector of A for the eigenvalue lambda. Now, x is non-zero in this definition, and you can think about why it is important that we require x to be non-zero in this definition here when we define eigenvectors and eigenvalues, and I will let you figure that out yourself, why it wouldn't make sense to allow x equal to 0 in this definition. Here's an image for this. So suppose this x is an eigenvector for the matrix A. This would mean if we apply A to x, then the result would just be some multiple of x. So for example, here x is mapped to 2x, so the eigenvalue would be 2. For the eigenvector x. And if some vector y is not an eigenvector, that means that if we multiply it by a, the resulting vector would not be a multiple of our original vector y. So it's actually a very, very simple idea. Accordingly, we can define eigenvectors and eigenvalues for linear maps. So if our linear map is called phi, then if there exists a vector x that is not 0 and some scalar lambda such that we have phi of x is equal to lambda x, then we call x an eigenvector of phi for the eigenvalue lambda. Again, a little graphic to illustrate this. So suppose we have two vectors v1 and v2 here, and phi maps them in a way that phi of v1 is just a multiple of the original v1. Again, I just picked the number 2. It could be some other multiple. But phi of v2 is not a multiple of the original v2, so this means v2 is not an eigenvector, whereas v1 is an eigenvector. And note, which may be not too surprising, the eigenvalues of a linear map phi are precisely the eigenvalues of a matrix A representing this linear map phi in any basis B. And that this is independent of the choice of basis will become evident later in this chapter. But unsurprisingly, the representation of the eigenvectors, the coordinate representation, will change if we change the basis. And because a lot of people wonder about the curious name eigenvalue and eigenvectors, let me tell you where this prefix eigen actually comes from. It is in fact a German word that, in the context that we are currently in, is best translated into English as characteristic. So this name comes from the fact that eigenvalues characterize the linear map to a great extent, though not completely. So there's a little bit of freedom in the characterization, even if we know the eigenvalues. We will see that more precisely later. And so in older English texts, eigenvalues are still often referred to as characteristic values. But for some reason it has become more popular to use this German phrase, eigenvalue, in newer literature. And now I have to actually make a remark on the scalars we're using in our plane and for our vectors. So up until now, almost everything that I discussed here did not require us to make an explicit choice for the domain of the scalars that we admit as coefficients for our vectors or that we multiply our vectors by. One exception where we would have to choose particular scalars is when we look at the rotation matrices, because their coefficients include terms such as sine alpha or cosine alpha, and these values have to be chosen from the real numbers. So whenever we look at rotation matrices, we have to assume that the scalars are taken from the real numbers, or anything containing at least the real numbers. And of course, all the images I draw to illustrate the concepts in this course strongly suggest that we use real numbers as coefficients. But still, we could imagine using other domains for our scalars, such, for example, rational numbers, that is just fractions, finite fields, so scalars that only allow finitely many values, or complex numbers. And except for some very special cases, everything we have proved in this course so far would still hold for all of these different domains of scalars. A notable exception being finite fields of characteristic 1, because they would have the weird property that the scalars would satisfy 1 plus 1 equal to 0, and a lot of things go wrong if you allow that. But chances are you have never heard of these fields anyway, and we're just imagining real numbers as scalars anyway, so we keep thinking about it like that. And when we're studying eigenvalues, we will see that we need to be more explicit about which scalars we admit for our vectors and matrices. So in this chapter, I will only consider the cases where our scalars are either real numbers or complex numbers. And I will use the letter K to denote the domain for my scalars when it could be either the real numbers or the complex numbers. So when I'm not deciding which one to pick, and when everything I say would be valid for either one. And if you're not familiar with complex numbers, you can ignore anything I say about them, or you look up the properties whenever I use them in this chapter. If you choose to ignore everything I say on complex numbers here, you would be at a loss, but the rest of the chapter will still make sense to you, so you could do that. Let's look at examples. So here we have a matrix over K, so as I said, this could be over the real or the complex numbers, which has these entries here, so 2, 0, 1, 1. And let's see what happens here. If I multiply A by the first standard basis vector E1, I get the vector 2, 0, which is 2 times the vector 1, 0, so 2 times the first standard basis vector. And this means that E1 is an eigenvector for the eigenvalue 2. Here, the multiple of E1 is the image under the matrix A. With E2, it looks a bit different. So A times E2 equals the vector 1, 1. So just the second column of A. That is this vector here, and this indicates that E2 is not an eigenvector because the result under multiplication by A is not a multiple of E2, but rather a proper linear combination of E1 and E2. The next example is a rotation matrix, and here I explicitly assume that we're looking at real numbers as scalars. And you remember this from previous lectures. R alpha, the rotation matrix for angle alpha, is cosine alpha, sine alpha, minus sine alpha, cosine alpha. And what happens here is that any vector x is rotated by an angle of alpha if we multiply by this matrix. And this means we do not have any eigenvalues if alpha is different from a multiple of pi. We do get an eigenvalue minus 1 if alpha is k times pi, so a multiple of pi, for an odd number k. Because in this case, as you can check using trigonometric identities, the rotation matrix is simply minus 1, 0, 0, minus 1, so it's minus times the identity matrix, so every vector in the plane is mapped to its negative. This is just a rotation by pi, or 180 degrees. So minus x is on the same line as x, so it's an eigenvalue minus 1 for every single vector in the plane. So the whole plane consists of eigenvectors. And another situation is that we have an eigenvalue plus 1 if the rotation angle is an even multiple of pi, because in this case we do a full 360-degree rotation, so the rotation matrix actually turns out to be the identity. So nothing happens at all with any vector. So every vector is just multiplied by 1. And this means again that every vector in the plane is an eigenvector. Now the question is, given any 2 by 2 matrix A, how can we find eigenvalues and eigenvectors of A? And for this we make some simple observations. If Ax equal lambda x, so this is our eigenvector or eigenvalue equation, then this equation is equivalent to 0 equal to lambda x minus Ax, simply by subtracting Ax on both sides. And this we can write somewhat redundantly as 0 equal to lambda times identity matrix times x minus Ax. And this we can again write as 0 equal to the matrix lambda identity minus A multiplied by the vector x. So we have this matrix here, lambda identity minus A. And if this matrix gets multiplied by x, then we get the 0 vector. And this means that lambda being an eigenvalue of A is equivalent to the existence of some non-zero vector in the kernel of this matrix here. So in the kernel of lambda times the identity minus A. And we have seen in the previous chapter on determinants that the condition that the kernel of some matrix being not just a 0 vector means that the determinant of this matrix has to be 0, which means it's not invertible. So we see that lambda being an eigenvalue of A is equivalent to the determinant of lambda times identity minus A being equal to 0. And this is true precisely for the zeros of this polynomial here. So these are the eigenvalues of this polynomial determinant lambda identity minus A. It might be a bit confusing for you to hear about some polynomial now. Let me introduce this properly. Let's take lambda to be some undetermined variable. And then we say the expression which I call f index A, determinant of lambda times identity minus A, is called the characteristic polynomial of the matrix A. We call that usually the determinant of a matrix just gives some number, but if the matrix itself here contains some variable lambda that is not specified yet, then what we get out of the determinant will also contain this lambda, and thus will be some algebraic expression in this variable lambda. And this is just a quadratic polynomial, which we call the characteristic polynomial of the matrix A. And what we just proved on the previous slide with our equivalences is the following theorem. If A is a matrix, then first, the eigenvalues of A consist of the zeros of the characteristic polynomial Fa. And second, if we introduce the notation E lambda A to be the x, the vectors in the plane, such that A times x equal lambda x, which is the same as the kernel of the matrix lambda identity minus A for some scalar lambda, then we have that this space E lambda A is different from 0 if and only if lambda is an eigenvalue for A. We see that this is an important subspace of the plane. So if this is actually different from 0, then it contains all the eigenvectors of A for the eigenvalue lambda, and in addition the 0 vector. And we then call E lambda A the eigenspace of A for the eigenvalue lambda. Let's return to the two examples that we studied previously and study them more systematically now that we know how to compute eigenvalues. First, let's compute the characteristic polynomial of this matrix here. So what we do is we take lambda times identity minus this matrix and then compute the determinant of that. This is lambda identity minus A, just gives this matrix, and the determinant by the usual formula for the determinants, where we have the product of the diagonal elements minus the product of the off-diagonal elements, which is just 0 in this case. So we obtain the characteristic polynomial lambda minus 2 times lambda minus 1. So it's a product of these two linear factors here with the variable lambda. And the zeros of this polynomial can be read off directly from this form. You have 1 as a 0. If you plug in 1 here, this becomes 0, and so the whole thing vanishes. Or if you plug in 2 here, then you get a 0 here, and the whole thing vanishes, so the second eigenvalue is 2. Then we compute the eigenspaces for these two eigenvalues. First, for the eigenvalue lambda 1 equal to 1. How do we do this? This eigenspace is the kernel of eigenvalue times identity minus a. So in this case, just 1 times identity minus a. So we can just plug in 1 here to get the matrix. So the kernel of the matrix minus 1, 0, minus 1, 0. And now, if you have forgotten how to handle these linear systems and how to compute kernels, then please review chapter 3 of this course on linear equations again. So the solution space of this matrix here, the kernel, is simply the set of all multiples of the vector 1 minus 1. So any scalar multiple of this vector is a solution for multiplying this matrix here and obtaining 0. So this is the kernel of this matrix, and thereby this is the eigenspace for the eigenvalue 1. All the vectors that get mapped to themselves under the matrix A. And similarly, we compute the eigenspace for the eigenvalue 2. So now we take the kernel of 2 times identity minus A, which, if we plug in 2 here, we get this matrix, and the kernel for this is the multiples of the first standard basis vector. So this is consistent with what we observed in the just graphical analysis of this map that we did before. We already found this eigenvector here, 1, 0, by visual inspection, but we had not noticed that there was a second eigenspace for the eigenvalue 1, which is generated by this vector here. So with the systematic approach via the characteristic polynomial, we could find this additional information that we didn't see at first glance before. Let's look at the other example, the rotation matrix, and now I explicitly state that we take it to be a real matrix in the real plane. And again, we first determine the characteristic polynomial of this rotation matrix. So we take lambda times identity minus this, obtaining this matrix, and then we take the determinant, which is this multiplied by this minus this multiplied by this. And then we get lambda minus cosine squared plus sine squared. We expand this and end up with this expression. And as usual, cosine squared plus sine squared, it just equals 1. So the resulting characteristic polynomial is lambda squared minus 2 times lambda cosine alpha plus 1. And the zeros of this quadratic polynomial are, using some formula you learned in school, cosine alpha plus minus square root of cosine alpha squared minus 1. So this is just the same as cosine alpha plus minus sine alpha squared. And now sine alpha squared is always a non-negative expression. So with the minus sign, what we have under the square root here is always a non-positive expression. So this will be cosine alpha plus minus I times sine alpha. So the square root for the minus 1 introduces this imaginary number I times the square root of the real factor sine alpha squared, which is just sine alpha. So the zeros of this characteristic polynomials are in general complex numbers. And they are only real numbers if this part here, the sine, is equal to 0, because then this imaginary part here in the back disappears. And well, when is a sine function 0? That's precisely the case if the argument alpha is a multiple of pi. And here we reproduce what we already derived before from geometric considerations. If we have an odd multiple of pi, then we get lambda equal to minus 1, because in that case, well, the sine vanishes and the cosine is negative. Or if we have an even multiple of pi as the rotation angle, then we get lambda equal to 1, because in that case the cosine is 1 and the sine again vanishes. So these are the two cases of a half rotation and a full rotation that we already saw before. And another thing we can do with this example is we pretend that this matrix is actually not a real matrix, but a complex matrix, and we apply it to vectors in the complex plane, by which I mean here vectors that have two complex entries. And in this case, the two zeros of its characteristic polynomial, which are the first one, cosine alpha plus I times sine alpha, and cosine alpha minus I times sine alpha, are perfectly legitimate complex eigenvalues, and we can compute the eigenspaces for them. So the eigenspace for the first eigenvalue, which is this one, is as usual computed as the kernel of lambda 1, the eigenvalue, times identity minus our rotation matrix. And this, well, you have to do a few computations, but then you see that this matrix here is I times sine alpha minus sine alpha, and again I times sine alpha. And doing a bit of work, simplifying the corresponding system of linear equations, you find that the solution space here, so the kernel, is all the multiples of the vector 1 minus I, where the multiples can be taken any complex factor zeta. And similarly, we compute the eigenspace for the second eigenvalue, lambda 2 equal to cosine alpha minus I sine alpha. Again, we multiply identity by the eigenvalue, subtract our rotation matrix, and compute the kernel. So the resulting matrix is this one, and applying our knowledge on how to solve linear equations, we find that the set of solutions here, namely the kernel, is all complex multiples of the vector 1 I. So in summary, even though this matrix here does not have any real eigenvalues and eigenvectors unless alpha is a multiple of pi, it does have some complex eigenvectors and eigenvalues. So here you see that it really does matter what scalars we allow as our coefficient set, because depending on that we can make a statement that eigenvalues and eigenvectors exist or do not exist. Now you can do some work yourself, and this will actually be a bit of a more involved exercise, so you might have to pause the video for a bit longer to do that. But here I give you a reflection matrix A, which looks a bit similar to the rotation matrix, but the minus sign is actually in a different spot. So it's cosine 2 alpha, sine 2 alpha in the first column, and in the second column sine 2 alpha minus cosine 2 alpha. And you may recall we already studied these a while ago in a previous chapter. And this is a reflection perpendicular to an axis that encloses an angle of alpha with the first coordinate axis. And what I want you to prove is that this matrix here has eigenvalues plus 1 and minus 1, and also compute the eigenspaces for the plus and the minus 1 eigenvalues. In doing so, you have to wrangle some trigonometric expressions, so I suggest you use the identities here. Cosine 2 alpha is equal to cosine squared minus sine squared, and sine 2 alpha is equal to 2 times sine alpha cosine alpha. Now, the solution, and I hope you really tried hard to find it yourself, is that the characteristic polynomial of our matrix A is determinant of lambda identity minus A, which is the determinant of this matrix here. We just use the usual formula for the determinant to compute it. So we have lambda times lambda minus cosine 2 alpha times lambda plus cosine 2 alpha minus sine 2 alpha squared. And this turns out to be just lambda squared minus 1 if you expand this product and combine cosine squared and sine squared to 1. So we get a very simple characteristic polynomial, and now it's obvious that the zeros of this polynomial and thereby the eigenvalues of A are just plus 1 and minus 1, because if you plug in plus 1 or minus 1 for lambda here, then you get clearly 0. Computing the eigenspaces is a bit nasty here, so you probably have to use these trigonometric identities for this. I'm not going through it in every detail, but just give you the end result. So for the eigenvalue plus 1, the eigenspace is the kernel of this matrix here, 1 times identity minus A. And after simplification, this is the kernel of this matrix here, which means it's all the vectors that are multiple of the vector cos alpha divided by sine alpha and 1. If you want, you can simplify this expression to the cotangent of alpha, but we don't really need to do that here. And similarly, for the eigenvalue -1, you find the eigenspace to be all the multiples of the vector minus sine alpha divided by cosine alpha and 1. And again, this could be written shortly as the tangent of alpha. The example from the previous exercise can be visualized in a nice way. So suppose we have the linear map sigma of x equal a of x, where a is our reflection matrix. And these are the two eigenspaces. So the blue one should be the eigenspace for eigenvalue +1, and the orange one should be the eigenspace for eigenvalue -1. Then what happens is every vector on the blue line here will just be mapped to itself because the corresponding eigenvalue is 1. And every vector on the orange line here will be multiplied by -1 and mapped to that. So it will just be flipped over to its negative with respect to the origin. And an arbitrary vector in the plane, let's say x, can be written as a linear combination of a vector on this line and a vector on this line. So it has this orange dashed line here, a component parallel to the -1 eigenspace, and the blue dashed line here, a component parallel to the +1 eigenspace. And if we apply the matrix A to it, what happens is the component in the eigenspace one direction will just be preserved because this part is multiplied just by 1, so it doesn't change at all. You see that here. But the component along the -1 eigenvector direction will be multiplied by -1, so it will be flipped over with respect to the blue line. So this part here becomes this part here. And so you see the effect that this map has on any vector in the plane is just reflecting it perpendicularly to the blue line. And algebraically, what this actually implies is that if we pick a basis in the plane where we take one basis vector from the +1 eigenspace and one basis vector from the -1 eigenspace, then the matrix that represents this linear map sigma in this basis is given by this matrix here. So 1, 0 and 0, -1. And you may recall that originally we looked at reflections about the first or the second standard coordinate axis, and they always had this simple form that they just had 1 or -1 on the diagonal, whereas reflections about arbitrary axes looked more complicated with all these cosines and sines. But here, by changing our basis actually to the corresponding eigenspaces, we see that with respect to these new coordinates, every reflection can be made to look in this very simple way. And this example already suggests a little bit that we can describe the effect, the geometric effect of matrices via their eigenvalues. And this is something we want to explore in depth now. In the last example, it was indeed the fact that the two distinct eigenvalues, plus and -1, and their eigenspaces completely determined what this linear map did in the plane. And we will now explore to what extent that actually holds for arbitrary linear maps or matrices. The coordinates of the eigenvectors, of course, depend on the chosen basis representation of a linear map, but the eigenvalues of a linear map are independent of the basis in which we represent it. And to see this, we do practically the same thing that we did in the previous chapter when we proved that determinants of a matrix or of a linear map do not change under a change of basis. And yeah, we basically reuse that argument here. So suppose A is a matrix that represents a linear map phi in some basis B. And suppose there's some other basis B tilde and T is the change of basis matrix from B tilde to B. Then we compute characteristic polynomial of the matrix A is by definition lambda times identity minus A. And now, from what we know about determinants, because they are invariant under conjugation, the determinant of this matrix here does not change if we multiply it on the left by T inverse and on the right by T. This is something we learned in the previous chapter. This is simply a property of determinants. Now we pull the T inverse and T into this expression here. So we get the determinant of lambda times T inverse T minus T inverse A T. These two just cancel out to give the identity. So we have the determinant of lambda times identity minus A tilde, where A tilde should simply denote the matrix representing phi in the basis B tilde, which is just obtained by conjugating A by this change of basis matrix. And then this, by definition, is simply the characteristic polynomial of A tilde. So we see that the characteristic polynomial of the matrix A that represents phi in some basis B equals the characteristic polynomial of the matrix A tilde that represents phi in some other basis B tilde. And that holds for all possible bases. And that proves that the characteristic polynomial is indeed independent of the basis we choose to represent some linear map phi. And that justifies defining the characteristic polynomial f phi of a linear map phi just via the characteristic polynomial of any of its representation matrices and computing the eigenvalues of phi via any representation matrix of phi is also justified by this. Now we want to attempt a classification of linear maps via the eigenvalues, but before that we need to do some preliminary work, and we start by getting a better understanding of the characteristic polynomial. So first a little digression on polynomials in general, or in particular quadratic polynomials. So suppose lambda squared plus alpha lambda plus beta is a quadratic polynomial with coefficients alpha, beta, and k, so either real or complex coefficients, where lambda is our variable and alpha and beta are taken to be some constant numbers. And if lambda 1 is a zero of this quadratic polynomial f, then the polynomial division of f by the linear polynomial lambda minus lambda 1 yields the following form of f equal to lambda minus lambda 1 times g plus r, where r is the remainder of the polynomial division. So this has to be of a lower degree than this one, so it has to be a scalar because this already has degree 1 and the scalar has to have degree 0. And g is some other polynomial of degree 1, so of a similar form to this. And this is of degree 1 because the product of lambda minus lambda 1 and g must have degree 2, so if g had a higher degree, then the product would have a degree higher than 2 and thus could not yield the polynomial f. But now our assumption was that lambda 1 is a zero of f, so we have 0 equal to f of lambda 1. But then if we plug in lambda 1 here, that means we get lambda 1 minus lambda 1, which of course is 0, times g of lambda 1, whatever that is, 0 times whatever, plus r, just leaves r. And this shows us that r is equal to 0. The remainder of the polynomial division of f by lambda minus lambda 1 is 0. And that means that f is in fact of the form lambda minus lambda 1 times some other linear factor lambda minus lambda 2, which would be our g. So it's just a product of two linear factors. And it is possible that lambda 1 and lambda 2 are identical. They don't have to be, but this is not excluded by this form here. Next, we define the discriminant of a quadratic polynomial, lambda squared plus alpha lambda plus beta, as this f equal to alpha squared minus 4 times beta. And if zeros of our quadratic polynomial f exists, then they are given by the formula lambda 1 and lambda 2 are equal to minus alpha plus minus square root of the discriminant divided by 2. And this is a formula you have learned in school. Don't tell me you haven't. You definitely have learned this formula in one or the other guys in school. Maybe you didn't call this the discriminant but wrote out this part here explicitly. That might well be. But I'm not going to prove this because you should be familiar with this formula. But what this tells us is that the discriminant determines the existence and the number of zeros. So what's under this square root here is decisive for existence and numbers of the zeros of a polynomial. First, we look at the case where our scalars are complex numbers, and here it is always the case that f is equal to such a product of two linear factors, as we have seen on the slide before. And that is the case because every complex polynomial has a zero in the complex numbers. And this is a special case of the so-called fundamental theorem of algebra. So the special case being that in this case we just have a quadratic polynomial, and it's probably not too difficult to show it in the quadratic case for complex numbers, but the fundamental theorem of algebra would actually say that any polynomial of any degree always has a zero in the complex numbers. Now we have two cases here. Either that the discriminant, this part here, is 0. In that case, this bit here vanishes, so we are left with one eigenvalue, lambda 1 equal to lambda 2, and we say that this eigenvalue has multiplicity 2. So that means that f is the product of lambda minus lambda 1 with itself. So this linear factor appears twice in f, and that's why we say it has multiplicity 2. The other case is where the discriminant is non-zero. So we have two distinct zeros then, lambda 1 and lambda 2, depending on whether we pick plus or minus here. And that's the cases for the complex numbers. In the real numbers, we have actually three cases to distinguish. The first is similar to the complex numbers. Here we have 1, 0, lambda 1 equal to lambda 2 with multiplicity 2. And in this case, f is equal to lambda minus lambda 1 squared. And for the real numbers, we can't just distinguish between discriminant 0 and non-zero, but we actually have to distinguish between 0, larger than 0, or less than 0. If the discriminant is larger than 0, then this root exists as a real number. And that means we have two distinct zeros, lambda 1 and lambda 2. And therefore our polynomial is lambda minus lambda 1 times lambda minus lambda 2, a product of two distinct linear factors. However, if the discriminant of f is less than 0, this would get a negative sign, so it would not exist as a real number. It only exists in the complex numbers. So that means that no real 0 exists for f, and therefore f does not have any linear factor. So we cannot simplify it further beyond this quadratic expression here. Now let's get back to the characteristic polynomial of a matrix. First we introduce the trace of a matrix, and this is something very simple. It's just the sum of its diagonal elements. So the trace of this matrix A here is just A11 plus A22. As an exercise for you, I ask you to prove that the characteristic polynomial of this matrix A is fa equal to lambda square minus the trace of A times lambda, so minus this times lambda, plus the determinant of A. And this then directly implies that the discriminant of the characteristic polynomial is trace A squared minus 4 times the determinant of A. And we can show this by direct computation. So by definition, fa is the determinant of lambda identity minus A, so this matrix here. If we compute this, we get lambda minus A11 times lambda minus A22 minus A12 times A21. Now we multiply out these two factors here, so we get, if we collect the terms, lambda square minus A11 plus A22 lambda plus A11 A22 minus A12 A21, and then we see directly that this here is the trace, and we recall that this is the determinant of the matrix A. So we have established this nice formula here, so we can, if we know the trace and the determinant, immediately write down the characteristic polynomial. That might sometimes be easier than computing it in this way, and from this we can immediately read off the discriminant. Another thing about the characteristic polynomial is a curious identity that's called the Cayley-Hamilton Theorem. And this states that if A is a matrix with characteristic polynomial Fa, then if we plug in the matrix A into its own characteristic polynomial, we will obtain the zero matrix. So we write this as Fa of A equal to 0. So what we mean by this is that we substitute the matrix A for the variable lambda in Fa, and then we use matrix multiplication and addition in the polynomial. And for the constant term in the polynomial Fa, we simply substitute the identity matrix as the zeroth power of A, if you like. And the proof of this goes by direct computation, like so many things here. And now we actually use our nice formula we just derived. So Fa applied to the matrix A itself equals A squared minus trace of A times A plus determinant of A times the identity matrix. And we write out these three terms here. So A squared is just this. Minus trace of A times A gives this. And determinant of A times identity gives this. And now you can just compare coefficients in each entry of the three matrices. If you add them up, I have highlighted them in matching colors. So you see that in each coefficient, the parts in matching colors just cancel each other out. So the A11 squared here cancels with the A11 squared here. The A12, A21 here cancels with the A12, A21 here. And the minus A11, A22 here cancels with the A11, A22 here, and we're left with 0. And similarly, you can check this for all the other coefficients that this holds, so they all cancel out. And therefore we see that indeed this expression here gives you the zero matrix. And this is the statement of the Cayley-Hamilton Theorem. You can imagine that something like that is much harder to prove in higher dimensions, where the theorem also holds. Here in dimensions 2 we can do it with a simple, if tedious, computation, but in higher dimension the proof is actually quite tricky and requires a bit of theoretical reasoning. Now we turn to classifying linear maps, or at least try to classify linear maps via their eigenvalues. And we begin with the following observation. Proposition 5. Suppose our matrix A has two distinct eigenvalues, lambda 1, lambda 2, and that b1, b2 are eigenvectors for these two distinct eigenvalues. Then b1 and b2 are linearly independent, and so b1, b2 form a basis of the plane. In short, eigenvectors for distinct eigenvalues are always linearly independent. The proof is as follows. So by definition, b1 and b2 are both non-zero because they're eigenvectors. So we said that eigenvectors by default are not zero. But suppose, for contradiction now, that they are linearly dependent. So for example, that b2 is a multiple of b1, so alpha b1 equals b2. And then we can actually write lambda 2 b2 equal to a b2. This is just because b2 is an eigenvector for the eigenvalue lambda 2. But now we can substitute this expression for b2 here. So we get a times alpha b1. And now we use that we can, well, commute alpha and a. And we use the fact that b1 is an eigenvector for the eigenvalue lambda 1. So this becomes lambda 1 times alpha b1. But now we can use this substitution here again. So we can again replace alpha b1 by b2. So we have, this is lambda 1 b2. So in total we have lambda 2 b2 equal to lambda 1 b2. But this implies that we subtract lambda 2 b2 on both sides, that lambda 1 minus lambda 2 times b2 is equal to 0. But b2 is not the zero vector by assumption. So this would imply that lambda 1 is equal to lambda 2, so because we need a factor 0 here. But this is a contradiction because we assumed these two eigenvalues to be distinct from one another. So our assumption that the eigenvectors for distinct eigenvalues could be linearly dependent has led to a contradiction. Therefore, they must be linearly independent. And from that, it immediately follows that b1 and b2 form a basis of the plane, a basis of eigenvectors. Now let's begin classifying linear maps by their eigenvalues. And we begin with complex linear maps of the plane. So let A be the matrix representing a linear map phi in the complex plane, and Fa its characteristic polynomial. Case 1. The discriminant of Fa is different from 0. In this case, A has two distinct eigenvalues lambda 1, lambda 2. So recall, as we just observed a while ago, that for a non-zero discriminant, the polynomial has distinct zeros. So here we have two distinct eigenvalues. Now, we pick any two eigenvectors b1 and b2 for those two distinct eigenvalues. And by the proposition we just proved on the previous slide, we can form a basis made up out of those two eigenvectors. In this basis, the eigenvectors b and b2 themselves are represented by the canonical basis vectors. That's pretty much the definition of a basis representation. So the first basis vector is represented by the first canonical basis vector, and the second eigenvalue basis vector is represented by the second canonical basis vector 0, 1. And accordingly, any matrix representation of the linear map phi in this basis B is of the form rho BB of phi, lambda 1, 0, 0, lambda 2. Okay, think about it. The eigenvector B1 is represented by this. So if we multiply this by the representation matrix for this basis B, we should get lambda 1 times this vector here. And we get that precisely by having lambda 1, 0 as the first column of our matrix. And similarly for the second eigenvector, we should get lambda 2 times this, and that is obtained by getting 0, lambda 2 in the representation matrix. So by changing to this coordinate system that consists of eigenvectors, we get a very simple form of this linear map phi, and we see that it acts by scaling along the two coordinate axes. Coordinate axes being given by the two eigenspaces generated by b1 and b2. And the scaling factors are just the eigenvectors of the linear map phi. And such a linear map that by an appropriate change of basis can be turned into a diagonal matrix is called diagonalizable. That was the first case for complex linear maps. Now let's go to the second case. This is the case where the discriminant of the characteristic polynomial is 0. And in this case, A has only one eigenvalue, lambda 1. And here we must distinguish two subcases depending on the dimension of the eigenspace for this single eigenvalue. So case 2a is discriminant of characteristic polynomial is 0, and the eigenspace for this eigenvalue lambda 1 is the whole plane. So this means that the kernel of lambda 1 times identity minus A is the whole plane, which is just another way of saying that A is equal to lambda 1 times the identity matrix. Because if the kernel of this is the whole plane, this just means that this is the 0 matrix, and then we get this identity that A is equal to lambda 1 times identity, so it's just this diagonal matrix here. So phi acts by scaling every vector in the plane by a factor of lambda 1. This is a very special case of a diagonal matrix, or a diagonalizable matrix, if you like, because this matrix form is actually invariant under any change of basis, which you can easily see by just conjugating A by an invertible matrix. So T inverse times A times T is T inverse times this times lambda 1 identity T. But this is just lambda 1 times T inverse T, and this again reduces to the identity. So no matter how we change the basis, this is always the same representation matrix because it's just a multiple of the identity. Let's look at the other case now. We still assume that the discriminant is equal to 0, and so we only have one eigenvalue. But now we assume that the eigenspace is not the whole plane. That means the eigenspace for the eigenvalue lambda 1 is just a line through the origin. And in particular, this means that there exists some vector that is not 0, that is not contained in this eigenspace, and thereby linearly independent to all the eigenvectors, because it's not on the same line, it's not a scalar multiple. by the Cayley-Hamilton theorem that we just proved previously, we have the identity that the zero matrix is equal to characteristic polynomial applied to A itself. So the matrix lambda 1 times identity minus A squared is equal to 0, because we know that in the case of discriminant equal to 0, so only one eigenvalue, our characteristic polynomial is just the square of a single linear factor. With A plugged in, we get lambda 1 identity minus A squared as the characteristic polynomial applied to A, and by Cayley-Hamilton this is 0. Now what this means is, if we rewrite it a little bit, 0 equal to 0 matrix times vector C, so this is the 0 vector now. We've seen by Cayley-Hamilton that this is a 0 matrix, so obviously any vector C multiplied by 0 matrix gives the 0 vector. And this we can write as lambda 1 identity minus A times lambda 1 identity minus A times C. And that shows us that this vector here, C multiplied by lambda 1 identity minus A, is actually in the kernel of lambda 1 identity minus A, because it gives you 0. So we can write B for this vector here, lambda 1 identity minus A times C, and because this is, by this equation here, in the kernel of lambda 1 identity minus A, this B is actually an eigenvector of the eigenvalue lambda 1. And it is non-zero, because if it was 0, then C itself would be an eigenvector, but we just assumed C to not be an eigenvector. So we have two non-zero vectors, B and C, one of which, namely B, is an eigenvector, and the other one, C, is not. And what follows is that if we multiply A by C, then we get AC is equal to lambda 1 times C plus B. It's just from this equation here. And now we can write down the matrix representation of phi with respect to the basis formed by the vectors B and C. Namely, it's the following. The eigenvector B comes first, so it's represented by the vector 1, 0, gets mapped to lambda 1 times itself. So this just gives lambda 1 times the vector 1, 0 as the first column. And the vector C gets mapped to 1 times B, represented by the first coordinate, plus lambda 1 times C, represented by the second coordinate. So we get the column 1, lambda 1, as the second column for our representation of phi with respect to this basis. So again, we have a rather simple form, but it's not quite as simple as in the previous case, because we have this additional 1 up here. And this is in fact a linear map or a matrix that is not diagonalizable. So before we had diagonalizable matrices, but here we have an example of a matrix that you cannot diagonalize. Geometrically, what this means is that you have a scaling lambda 1, lambda 2 along the axis given by these two vectors here, but combined with a shearing that is parallel to the eigenspace that goes through B. These were the two complex cases, and now we look at the real case. So now we'll assume that A is a real matrix representing a linear map of the real plane, and Fa is again its characteristic polynomial. And the first two real cases pretty much follow exactly as in the complex case. So the first case here is now where the discriminant of the characteristic polynomial is positive. It's not just different from 0 as in the complex case, but we require it to be positive. This is the case where we have two distinct real eigenvalues, lambda 1, lambda 2. And in the same manner as in the complex case with discriminant different 0, we derive that we find a basis of eigenvectors such that in this basis phi is represented by the matrix lambda 1, 0, 0, lambda 2. So it's diagonalizable. Then the second case is when the discriminant of the characteristic polynomial is 0. And again, we have two subcases, case 2a being when the eigenspace for this single eigenvalue is the whole plane. Again, just like in the complex case, here phi is represented by a multiple of the identity matrix, so it's lambda 1 on the diagonal and 0 otherwise. And case 2b is discriminant 0, but eigenspace is not the whole plane. So just like in the complex case, we can find a basis in which we can represent our linear map by a matrix such as this, lambda 1, 0, 1, lambda 1. So the combination of a scaling along the axis combined with a shearing parallel to the eigenspace. And the really juicy case is the third case, where the discriminant is less than 0. This is going to be a bit complicated, so you have to be patient and focused, and maybe also work along a little bit with pencil and paper. In this case, we do not have real eigenvalues, as we discussed before, because a real polynomial with discriminant negative does not have real zeros. But to understand this case, what we will do is we will take our real linear map and extend it to a linear map of the complex plane C2. How do we do this? Well, instead of just restricting ourselves to real vectors, or vectors with real coefficients in this equation here, we allow vectors with complex coefficients for the matrix multiplication AX, and thus we get a linear map which I call phi C of the complex plane by simply reusing the same matrix. And to analyze this map, I will have to use a few properties of complex numbers that I will just state here. I will not bother to explain them much more because that would take way too much time. So as I said before, you can either choose to ignore this, or you can just choose to accept what I state here as a properties. You can try to derive it yourself or look it up somewhere, or perhaps you're even familiar with complex numbers and this is just all known to you. Anyway, the first property is that every complex number zeta can be written in polar coordinates. That is, for some suitable radius larger than 0, so a real number r larger than 0 and some angle alpha, we can write zeta as r times cosine alpha plus I times sine alpha. So this expression here with the cosine and sine, that's actually a complex number of absolute value 1. And if we multiply this by some radius r, we can scale it up and down to any complex number we like. Second, for every complex number zeta, there is its complex conjugate, which we call zeta bar. And we obtain this simply by flipping the sign of the imaginary part of the complex number. So if we write zeta like this in polar coordinates, its complex conjugate would simply be r times cosine alpha minus I times sine alpha. In particular, what you notice here is that if this complex number zeta is already a real number, so if the imaginary part here vanishes, then it would be unchanged under complex conjugation. So complex conjugation does not affect real numbers, it only affects complex numbers that are not real. And with the help of the complex conjugate, we get some elegant expressions for the real and imaginary parts of a complex number. Namely, the real part of zeta is just r times cosine alpha. And you can check this. This is the same as 1/2 times zeta plus zeta bar. And the imaginary part of zeta, which is r times sine alpha, is just minus I divided by 2 times zeta minus zeta bar. And important to note, both the real and imaginary part of zeta are actually real numbers. The imaginary part only becomes an imaginary number when you multiply it with I. But by definition, the imaginary part is always just taken to be that part that you multiply the I with, but not with the factor I itself. And now one observation about real polynomials into which we plug in complex numbers. So if f is a polynomial with real coefficients and the complex number zeta is a 0 of f, then the complex conjugate zeta bar is also a 0 of f. And I will just prove this for quadratic polynomials because for lack of space, but the statement holds for polynomials of arbitrary degree. And to see this, I plug in zeta into f, and this is by assumption 0. 0 is the same as the conjugate of 0, so 0 equals 0 bar. And this means this is the same as f zeta conjugate, obviously. Now I write this out explicitly, and here I assume that f is quadratic, but as I said, this would hold for polynomials of higher degree as well. So this is zeta squared plus alpha zeta plus beta. And now an important property of the complex conjugate that you cannot immediately spot from its definition, but which you can verify if you do a bit of work, is that complex conjugation is compatible with addition and multiplication in the complex numbers. So this expression here is actually identical to zeta bar squared plus alpha squared times zeta squared plus beta squared. And now we use that we assumed the coefficients alpha and beta of our polynomial are real. That means they're unchanged under complex conjugation. So this is in fact zeta bar squared plus alpha zeta squared plus beta, but this is nothing else than f applied to zeta bar. So with this reason here, we see that if f zeta is equal to 0, then f zeta bar is also equal to 0. So in particular, if we know for a real polynomial one complex 0, we automatically know a second complex 0, namely the complex conjugate of that complex 0. Let's continue to study our case 3. We know that the linear map phi c has a real matrix. So its characteristic polynomial fa has real coefficients. And by what we just proved, since fa has at least one complex 0, because of our initial assumptions this is not a real number, it must also have a distinct second 0, namely zeta bar. This means we have two distinct complex zeros for phi c. So in this case, we have case 1 for complex maps. That means we can find a basis, which I call c and bar c, of complex eigenvectors, such that in this basis, this extended map phi c is represented by this diagonal matrix, zeta 0 and 0 zeta bar. And the notation already suggests it. This vector c bar can be chosen as the component-wise complex conjugate of the first vector c. And to see this, observe that for any real matrix A, that's an argument similar to the polynomial now, for any real matrix A, if AC is equal to zeta c, then A times complex conjugate of C is the same as complex conjugate of A times C, because matrix A is real, so conjugation doesn't change it. This, by assumption, is complex conjugate of zeta times C. And because complex conjugation is compatible with multiplication, this is bar zeta times bar C. So this shows us that if C is an eigenvector for zeta, then as an eigenvector for zeta bar, we can just take the component-wise conjugate C bar. And this is what this notation should suggest. Our plan is now to find a clever change of basis from the complex basis C to a basis B of vectors that only have real coefficients. So we want to do a change of basis from a complex to a real basis in such a way that the resulting representation matrix of phi is also real, and that it is of a certain form that reveals its geometric structure for the original real linear map phi. And lo and behold, by divine intuition, we choose this as our real basis. We just take component-wise the real and imaginary parts of the first complex eigenvector C. So that means B1, first real basis vector, is 1/2 times C plus C bar. So just component-wise the real part of C, which automatically shows us that it is a vector with real coefficients. And B2 is minus I/2 times C minus C bar, which is just component-wise the imaginary part of C, and therefore also automatically a vector with real coefficients. Now, we have to do some calculations. The change of basis is given by these two matrices here. So the change of basis from C to B is given by 1i, 1 minus I. So this just corresponds to having the real and the imaginary part added up, the imaginary part with a factor of I, to give the vector C. And here it's for the complex conjugate C bar, where we just have a minus sign for the imaginary parts. So this you can easily derive from the way we constructed B1 and B2. And then the reverse change of basis, MBC, just has to be the inverse matrix of this one. And for example, you can quickly compute this using the explicit formula that we derived in the chapter on determinants. Now we write the eigenvalues zeta and bar zeta in polar coordinates, and then we perform the change of basis on row C, phi C. So this was just a diagonal matrix with C and bar C on the diagonal. And this way we get the representation of phi in the basis B. So this is given by applying the change of basis from C to B to the representation matrix in the basis C, and then applying the change of basis from B to C. So we multiply this matrix by the diagonal matrix where we write zeta, zeta bar in polar coordinates, and then multiply here with the other change of basis. This is a bit of work to do. I'll leave that as an exercise for you at home to work this all out, but in the end you are left with this matrix here. So row PB of phi, the representation in this basis here of the original linear map phi is given by R divided by 2 times the matrix cosine alpha minus sine alpha cosine alpha, and we keenly observe that this is just the rotation matrix by the angle minus alpha. So what we have done now is we have used this ingenious trick by taking a detour through the complex plane to study a real linear map, and have obtained the most fascinating result that a linear map of the real plane without real eigenvalues has a pair of complex conjugate eigenvalues, and that this real map actually is a scaling by the factor 1/2 times r, where r is this factor here, and a clockwise rotation about the angle alpha. So clockwise being indicated by the negative sign here. So now we actually have a geometric understanding of these real linear maps that do not have real eigenvalues. They are rotations combined with a certain scaling, and the degree of the scaling and the rotation angle are actually determined by their complex eigenvalues. And I think there's a really very beautiful connection between real and complex geometry here. So I stated at the beginning that we attempt to classify linear maps by their eigenvalues, but what we've seen in our classification now is that even though eigenvalues do convey a lot of information about the linear map, they're not completely sufficient for the classification. Because in one case, namely when the discriminant is equal to 0, we require as an additional information the dimension of the eigenspace for the single eigenvalue. So we have to know, is the eigenspace the whole plane, or is it just a one-dimensional line? And this is an information that we do not a priori get from the eigenvalues, so we need to do additional work to extract that information. In dimensions larger than 2, the classification of linear maps becomes much more involved, because as the dimension of the space n grows, the different combinations of eigenvalues and dimensions of the eigenspaces grow very rapidly with n. But such a classification is possible, and it eventually culminates in the theory called the Jordan canonical form of a linear map. And I would say this is one of the crowning achievements of linear algebra, because it gives you a really beautiful, even though somewhat difficult, theory of linear maps, at least over complex vector spaces, also over real vector spaces. And this is certainly a goal one should aspire to understand someday when studying linear algebra. Now, to end this section of the lecture, recall what you've learned so far about the characteristic polynomial and the classification to solve the following exercise. Let A be a real 2x2 matrix with negative determinant. Show that A is diagonalizable. And this is actually very simple once you know how to do it. We use our nice little formula for the characteristic polynomial here, lambda square minus trace A lambda plus determinant A. And then the discriminant of Fa is trace A squared minus 4 times determinant of A. And this is larger than 0. It's a positive number because by assumption our determinant is negative. So this part here is non-negative and this part here with a minus sign must therefore be positive. So because we have a positive discriminant, this is case 1 of the classification, in which we have 2 distinct eigenvalues, and this implies that A is in fact diagonalizable. Now we want to talk about applications of eigenvalues, and from what you've seen so far, you saw that eigenvalues are great for deriving theoretical results on linear maps, but in addition to that, they can also be applied to many practical problems. Usually, of course, these applications take place in dimensions much higher than 2, but we were restricted to 2 dimensions in this course, and I will just give a short overview over some of these amazing applications and then give you a worked out example of an application that can be expressed in a 2-dimensional setting. One example is the study of dynamical systems, so systems that evolve over time. So this could be differential equations or population simulations. And as a special case of this, the so-called stochastic processes given by Markov chains, where your state transitions are determined by certain probabilities. And this picture here suggests how such a dynamical system could work. So the vectors represent certain states of the system, and for example, if you have an eigenvalue which is less than 1 and an eigenvalue 1, then every vector is a linear combination of these two, and as you repeatedly apply the matrix A of this system to some state vector, it will eventually converge to an eigenvalue or to an eigenvector of eigenvalue 1. And this allows you to understand how over time such a state develops. Another application field is data analysis. For example, what is called principal component analysis. If you study data, which you can, in theory at least, plot along the axis for certain features, then there's a thing called the covariance matrix that you can compute, and the eigenvalues and eigenvectors of this matrix determine the directions of the strongest or weakest correlations of your data. And if you have many dimensions, that usually implies that the computer you're doing your work on has to do a lot of work, and by determining which dimensions are not very important for your data because they have weak correlation, you can throw out those dimensions and thus reduce the dimensionality of your data significantly and thereby make computations much easier. Other applications are semantic data analysis, which is basically taking natural language and mapping it into some kind of vector space, if you like, and then analyzing relationships between different words or word structures in this space. And also search algorithms such as Google's PageRank use eigenvalues very strongly. So in a way, they work a little bit like dynamical systems. One very ingenious application of eigenvalues and eigenvectors is the solution of recursive equations. So for example, something like this. You have a sequence of numbers xn, and the n plus first element of the sequence is given by a recursion a times xn plus b times xn minus 1, so depending on the 2 previous elements of the sequence. And you can cast such a recursion in matrix form, like this. You can check that this matrix multiplied by the vector xn x minus 1 just yields the vector xn plus 1 xn. So by multiplying repeatedly with this matrix, you generate the by the different elements of this sequence. And by studying eigenvalues and eigenvectors of this generating matrix here, you can actually find out closed form solutions for your elements here and need no longer rely on recursion. A huge field of application of eigenvalue theory is algebraic graph theory. What this means is you study graphs, such as this one, by assigning certain matrices to them. For example, the adjacency matrix or the so-called Laplace matrix. And these matrices describe connectivity properties of the graph. For example, without further explanation, this graph here has the Laplace matrix as this. And if you compute eigenvalues of this matrix, you find that the eigenvalue 0 occurs with multiplicity 3. So you have a linear factor lambda to the power of 3 in the characteristic polynomial of this matrix. And this means, which is of course not obvious at all, but this means that the graph has 3 connected components, as you can easily see from the picture here, the 3 connected components. Now, with such a simple graph, that might be obvious. You see it just by looking at it. But imagine your graph had a few thousand nodes, then of course this would not be so obvious to see. And yeah, there are a lot of other properties that you can derive by looking at eigenvalues of these matrices associated to a graph. Another application for eigenvalues is quantum computing, or, well, actually I should say quantum physics in general maybe. But in quantum computing, quantum states are elements of complex vector spaces, and every measurable quantity in quantum physics is assigned a linear map whose eigenvalues are the possible outcomes of measurements. And in computer science, for example, Shor's algorithm makes very ingenious use of this. So you want to compute the factorization of an integer n, which is very difficult to do in general on a classical computer. And this ingenious algorithm does this by encoding the order r of some number x modulus n as an eigenvalue of this form, so some complex exponential e to the power of 2 pi I k divided by r. And this is an eigenvalue of some complex matrix U, and then the so-called quantum Fourier transform makes it possible to estimate this eigenvalue, or this one part of the eigenvalue from this information. And now let's work through a concrete application, and what I will show you here is a simple predator-prey model as a dynamical system. And more precisely, we assume we have a given population of owls, OT, and a population of rats, RT, at time t, which I will measure in months. And yeah, the rats are measured in thousands of rats because there are so many of them, so kilo rats if you like. And what happens here is that the owls eat the rats, which reduces the rat population and increases the owl population. However, what can happen is that there are too many predators and too little food. So if there are too many owls and too few rats, then some owls will starve to death, which thus reduces their numbers again. And so then we have fewer predators, which allows the rats to thrive again, and so on. So you can already imagine that there's a certain back and forth going on here, with both populations maybe oscillating up and down a little bit. And to actually understand this precisely, we make up a mathematical model from which we can then derive the long-term development of the two populations depending on their initial state. So more formally, we formulate the rules for this predator-prey model as follows. If there are no rats at all, then the owls will starve, and this will reduce them monthly by a factor alpha, which is between 0 and 1. If there are rats, then the supply of food increases the owl population by a positive factor beta per kilo rats. So the more rats there are, the more the owl population thrives. The owls reduce the rat population by a quota of gamma, so gamma being a negative number then, and the absolute value of gamma should also be between 0 and 1 for each owl. And the rats procreate naturally, so every month their number increases by a factor of delta. Now you could complain that we don't have the natural procreation of the owls included in this model, but for simplification we assume they procreate very slowly compared to the rats. So yeah, we will just include implicitly the procreation of the owl in the supply of rats, and in the negative procreation, if you like, in the starvation if there are no rats. And these rules can be cast into two equations for the evolution of the two population, owl and rats. So in month t+1, the owl population is given by alpha times the previous owl population plus beta times the rat population. And the rat population in month t+1 is given by gamma times the owl population plus delta times the rat population in the previous month. Now we can write these two populations into a vector. So xt is the population vector which has owls and rats at month t as coefficients. And then this becomes a vector matrix equation. So ot plus 1 rt plus 1 is this matrix alpha, beta, gamma, delta times ot, rt, so the population from the previous month. To actually compute something, let's plug in some more or less realistic value for these matrix entries. So suppose that the rate of death by starvation for the owls in the absence of rats is 0.5. So every month 50% of the owls die if they don't have any food. The owl population increases per kilorat by a factor of 0.4, so beta is 0.4. The kill factor that every owl inflicts on the rat population is minus 0.1. And the natural procreation rate of the rats should be 10%, so the factor delta is 1.1. And let me stress, this is maybe not the most exact and realistic model. In particular, what you see is that if you start out with an owl population of 0, but you still have some rats, then you will actually, by virtue of this equation, obtain some owls out of thin air simply by the existence of rats. So obviously this is not perfectly realistic, but yeah, let's just accept this as a simplified model for the sake of demonstrating the technique of using eigenvalues. And with these parameters, our system's evolution matrix here becomes A equal to 0.5 minus 0.1, 0.4, 1.1. Now let us understand how eigenvalues can help us with understanding this system. So I'll first give you the general idea here, and then we will actually try this out for the concrete model. Every vector xt represents the state of the owl-rat population at a certain point in time t. Now suppose our evolution matrix A had an eigenvalue 1, and then of course a corresponding eigenvector b1. This eigenvector b1 represents a population of owls and rats that is stable over time, because if you evolve b1 from one month to the next, ab1, it's still the same. And if you evolve it twice, it's still the same. If you evolve it t times, it's still the same. So it never changes over time. So this would be an owl-rat population that is really stable. So the amount of killing and procreating that goes on is perfectly balanced out, so that both populations survive in the long term. Now on the other hand, if we have an eigenvalue less than 1, then this would represent a population which I call b less, in which the ratio of owls to rats is constant, but both populations decline monthly until they eventually die out. To understand this, if we multiply b less by a, let's say the eigenvalue is 0.1, less than 1, so we end up with 10% of the original populations for both owls and rats. If we apply this twice, a squared times b less, then we end up with 100th b less, so the population is already vastly reduced. And so if we continue over time, we get a to the power of t times b less is 10 to the minus t times b less. So you see the population declines very rapidly towards the zero vector, which is the state where both populations are extinct. And if two such eigenvectors existed, then any initial population x0 could be written as a linear combination of b1, the stable population, and b less, the extinction population. And from this, it then follows that as time passes, the initial population would converge towards the stable population. So you can see this sketched here in the diagram. So this is our owl axis and this is our rat axis. And if we have this initial population, and then we apply several times the matrix A to the initial population, so that means t months have passed. That's like applying A to this linear combination here. And this just means that the first part, the stable part, lambda b1 is unchanged, but the second part, mu times b less, becomes 10 to the minus t mu times b less, and as t goes to infinity, this part vanishes and we converge towards lambda b1. So some stable population along the axis of the eigenvector for eigenvalue 1. And this is indicated by this convergence of these arrows here towards the blue one. So for our concrete model, let's try this out. The characteristic polynomial for the values that we picked for the matrix A is lambda square minus 1.6 times lambda plus 0.59. You can check this by hand. Maybe a bit more difficult to check by hand is actually computing the eigenvalues. So I used a computer for that. And we find the eigenvalues to be approximately lambda 1 equal to 1.0236 and lambda 2 approximately equal to 0.577. So we more or less have the situation that I sketched before. So one eigenvalue is very close to 1 and the other one is less than 1. So the scenario I just explained before is likely to occur. The respective eigenspaces for these eigenvectors are given as follows. Again, use a computer to get that. So for the eigenvalue lambda 1, which is very close to 1, we get as an eigenspace the multiples of the vector with entries 6.07 and 7.95. And for the eigenvalue less than 1, we get as the eigenspace the multiples of the vector with entries 9.8 and 1.8. You can already see there's quite a difference here in the ratios of owls to reds. So here you have many more owls, and here they are not identical but are much more balanced in their ratio. So let's interpret these eigenspaces, what this means. If the ratio of owls to reds is this divided by this, so roughly 0.76, this is then the eigenspace for the eigenvalue lambda 1. Then the populations will remain stable over time and even slightly increase because this eigenvalue is actually even a bit larger than 1. So this would be a very healthy situation. You have two populations where one feeds on the others, but not too much, so that both populations can still grow. On the other hand, if we have the extreme case that the ratio of owls to reds is 9.8 to 1.8, so roughly 5.44, so this divided by this, then both populations are going to die out over time from overhunting and the ensuing starvation. So here you have way too many predators, so they kill off the reds too quickly and then starve themselves in the end. And for arbitrary owl to red ratios, which would be the case of a state that's a linear combination of the two, the ratio will eventually approach the stable ratio. So the vector representing this ratio will converge towards the eigenvalue that is slightly larger than 1. And that concludes our application and also this lecture on eigenvalues and eigenvectors. Please like this video and subscribe to my channel and stay tuned for more content. Thank you very much.